Module 2b of Unit 3 concerns reaction rate and temperature and introduces the idea of catalysis. You may have seen in the laboratory the fact that reaction rates increase with increasing temperature. You've heated something on a hot plate to speed a chemical reaction up. The relationship between reaction rate and temperature is the Arrhenius equation for the rate constant. Here we see the rate constant A on the left of the Arrhenius equation. And on the right hand side we have a pre-exponential factor, and then e to the negative of this fraction. The denominator of the fraction is RT, where R is again the gas constant in joules units. T will be temperature in Kelvin, and E is the activation energy. Typically, a one-step reaction proceeds by starting at the reactant, go to the products. This energy diagram shows that the products are lower in energy than the reactants. In other words, this is an exothermic reaction. In fact, the energy is around negative 300 kilojoules on this graph. However, to get from the reactants to the products, you must pass through an intermediate called a transition state. The transition state is a halfway point and is higher in energy than the reactants. Here we see that the energy of the transition state is 400 kilojoules above the reactants. So if you're breaking one bond and forming another, you may think of the transition state as around the midpoint at which one bond is breaking and the other bond is forming, for example. Notice that the reverse reaction will have a transition state as well, going from products back to reactants. The transition state from the reverse reaction, just doing the energy arithmetic of this graph, is 700 kilojoules. The x-axis shows progressive reaction from reactants to products. It's possible to do experiments to determine the activation energy. And essentially the idea, or the thing that must be done, is to measure the reaction rate of varying temperatures. If we only have two temperatures to work with, we can imagine a reaction rate K2 at temperature 2, described by the Arrhenius equation as A times e to the negative of the activation energy over RT2. We have another rate constant at a lower temperature, K1, which is equal to A times e to the negative of the fraction of the activation energy over RT1. Divide K2 by K1, and you will see that it's better to divide K at the higher temperature by K at the lower temperature. And you get the ratio of the Arrhenius expressions seen above. Take the natural log of both sides and you can produce the equation natural log of K2 over K1 equals negative EA over R, 1 over T2 minus 1 over T1. You can see an illustration of this in Averill, the free online text, example 13. Now, you will see that, if K2 is at the higher temperature, it's the larger rate constant corresponding to the faster reaction. So K2 over K1 is greater than 1, which means the natural log of K2 over K1 will be a positive number. Likewise, since T2 is larger than T1, negative EA over R will be negative 1 over T2 minus 1 over T1 will be negative, and the result will be, the resulting product of the two will be a positive number. Right, here we have an example that you could attempt before continuing concerning the conversion of cyclopropane. We have rate constants at two temperatures, 400 and 430 C, corresponding to 673 and 703 Kelvin. See if you can use this relationship to determine the activation energy and A, the pre-exponential factor. If we use the expression on the previous slide, the left-hand side is the ratio of the rate constants we're provided. Note that the units will cancel. And on the right-hand side, we have the negative of the activation energy divided by the gas constant times the difference of the reciprocal temperatures in the brackets. And we've noted before that this quantity in brackets will be a negative number. You see that when you take the difference of the reciprocals, 1 over 703 minus 1 over 673. Note that we use kelvins for temperatures. And we have a difference of negative 0.00007 Kelvin times negative E, the negative of the activation energy E sub A over the gas constant. Negative times a negative is a positive, so the right-hand side, or product of these two, will be a positive number. Left-hand side is the natural log of 8, well, the left-hand side is the natural log of 8.5. Natural log of 8.5 is 2.14, so we have 2.14 equals 0.00007 in reciprocal kelvins times the activation energy over R. It's best to solve at this point for the activation energy over R, which is 30,000 Kelvin. You can then multiply this number through by the gas constant. Note we use R in joules units, 8.314 joules over moles times Kelvin. And we get an activation energy in units of joules per mole. The same units of energy as the energy of reaction seen on the diagram or graph representing activation energy above. Well, to be correct, the graph had showed activation energy and energy of reaction in kilojoules per mole. You can solve for A using either one of the two data points at two temperatures provided. Here we have the Arrhenius equation. Take our K at 703 Kelvin, which we have as 1.1 times 10 to the negative 5 reciprocal seconds. Insert the activation energy we now know. Divide that by gas constant R, 8.314 times our temperature, 703 Kelvin. You should obtain a number of around 1 times 10 to the negative 15. When you solve for A is around 1 times 10 to the 10 reciprocal seconds. Alright, note units in the Arrhenius expression. A has the units for the reaction, reciprocal seconds, first order, typical first order reaction units we've seen. The energy units of the activation energy are joules per mole. You will sometimes see that converted to kilojoules per mole. So that the activation energy has units corresponding to an energy of reaction. This is a good point to introduce the idea of a catalyst. A catalyst is defined, and you'll see it defined in your text, as a substance that increases the rate of a reaction without itself undergoing any permanent chemical change. In other words, a catalyst is not a reactant or a product, but it's a chemical species present that speeds up a chemical reaction. One way of thinking about how a catalyst works, which is appropriate for this discussion, is in terms of activation energy and the energy profiles of reaction we've been looking at. Here again we see an exothermic reaction in which the reactants lose energy to go to products. However, there is an activation energy which must be overcome first. The more heat you put into the system in general, the easier it becomes to get over the barrier. We expect the reaction to go faster as it speeds up. The function of a catalyst, shown here, is to create another path with a lower activation energy. Ways to increase the speed of reaction are A, to increase the temperature, we've just seen that, or find a way to lower the activation energy. And a catalyst provides another reaction path with a lower activation energy, which results in a larger rate constant and a higher reaction rate. Other modules within the kinetics unit will show an example of a catalyst working to make a chemical reaction faster. A common catalyst you may encounter in biochemistry is the enzyme, which speeds up biochemical reactions, again by providing a reaction pathway with a low barrier or activation energy.